Hi and welcome to another episode from Spiral Education Physics, and what we're going to be looking at in this lesson is the dangers of static electricity. So we're going to be looking at lightning and sparks. We'll also be looking at refueling and the importance of earthing when fueling, and also the dangers of a build-up of static electricity in the operating theatre. But to start off with, it's important that you understand how static charges build up. You also need to know that it's just the electrons that move when we're dealing with static charges, and that if you do bring a charged object near another charged object, then that second object can become charged by the act of induction. And also be aware of the law of electrostatics. And if you're uncertain about any of those, do check out some of the videos on the channel to help you to get up to speed. So let's have a look at lightning then. And when we look at a lightning cloud, there's a very distinctive shape to that cloud. First of all, it's sort of like an anvil shape with a very, very flat top. So there's a massive convection current. They're very, very large clouds. And if we look closer at that, we see that there's cold air and warm air next to each other. And if we look about just at the boundary between them, they're trying to move past each other, and cold air, because it's denser, is going to get pushed down, trying to get underneath the warm air, and the warm air is going to get pushed up, and it will try to move above the cold air. So you've got this movement of air and a very, very clear boundary. Now, inside the thundercloud, what we have are hailstones, and on the cold side, they're a bit bigger and harder than on the warm side, which kind of makes sense. And when they're at the boundary, they're going to rub past each other, and so the large hailstones are falling, and the warmer ones are rising, the smaller ones. And this rubbing, this friction, generates static electricity, and the ones that are moving upwards, the lighter, squishier ones, become positively charged, and they rise to the top of the cloud. And the heavier ones, well, they're gaining electrons, so they become negatively charged, and they fall to the bottom of the cloud. So you get this distribution of charge because of these different sized hailstones. What's going to happen is that we're going to end up getting a distribution, a very, very clear distribution of charge at the bottom and at the top of the cloud. And if we take a look at that cloud as a whole, you can see that in this diagram. And what will happen is that over time, negative charge will build up at the bottom, and that will increase the voltage, or something called the potential difference, between it and the Earth. Now, it's okay to have a potential difference, and usually it's not going to be dangerous. For instance, a battery has a potential difference of 1.5 volts, which is very, very low. And under normal circumstances, air, which is an insulator, doesn't conduct electricity. However, at very, very high voltages, it can conduct electricity. You get a spark, and that's what this lightning is. It's a build-up of so much charge. The potential difference or voltage is so large that a spark's formed, which causes the air, which is normally an insulator, to conduct. So let's have a look at that in a little bit more detail. So you can imagine that we've got this bottom of this thundercloud being negatively charged. And if we look at the Earth, well, the Earth has got an equal amount of positive and negative charge. But as soon as that thundercloud comes anywhere near, it being negatively charged, we're going to have an induced charge effect here. So the electrons that are at the surface of the Earth, well, they're going to get repelled deeper into the surface of the Earth, and that's going to leave the very tops of the buildings and the Earth and the trees and anything that's on the surface with an induced positive charge. So we've got opposite charges there. And so that's not normally a problem unless this potential difference between the positive and the negative charge builds up and that voltage gets large enough so that it can make the air conduct. And when it conducts, you get a spark or lightning produced. And that's going to release a massive amount of energy. And the spark is so warm that it actually warms the air just around the spark, the lightning, and that air expands fasten the speed of sound, which breaks the sound barrier and causes a sonic boom or thunder. So obviously lightning is dangerous. There's so much energy, and people have survived lightning strikes, but there have been lots of people who have been killed by lightning strikes, so that's a massive danger. Okay, planes and static electricity. Well, planes, when they fly through the air, they rub against the air particles, and that can cause static electricity to build up, or static charges to build up. And it will remain on the plane because the plane is isolated from the Earth, so it's got nowhere for it to build up. So on a long journey, that charge will build up, and that potential difference, that voltage between it and the Earth, will get larger and larger and larger. And obviously, then a large voltage or potential difference, when given the opportunity, can cause a spark, which could ignite something. So, not a problem in the air. However, when the plane lands, it puts its wheels out, which are made of rubber, which are insulating. So technically that plane has still got a static charge because it hasn't been able to discharge. There's no way for that extra charge to get down to Earth. So you can imagine then that a fuel truck comes up and tries to put its fuel pipe into the airplane. And what happens then is that there's a massive discharge from the plane to the fuel truck, and there's an explosion. It ignites it, and that is very, very dangerous. So strangely enough, they don't do that. They have a safety procedure in place so that the plane doesn't explode, or the fuel truck doesn't explode. So instead, we've got a negatively charged plane, and we've got the fuel truck that comes up to the plane. And before the fuel truck does anything with the plane, it earths itself, which is this symbol here. So there's a metal wire attached to the earth. And then the fuel truck attaches a wire from it to the plane. And what that allows is any excess charge that's on the plane, that excess charge can then flow nice and safely down to Earth with no sparks, no ignition of fuel, no explosions. So that's the first danger averted. So then the fuel truck will attach a fuel pipe between it and the plane, and it will also earth that fuel pipe, because fuel flowing through a pipe was going to be static electricity building up, because you've got two insulators rubbing against each other. And again, if you've got a static charge building up on fuel, it could cause a spark, and that fuel could be ignited. So if there's any static electricity building up when the fuel flows through the pipe, then it's got a route for it to go down to Earth and discharge before it can have a chance to build up and increase that potential difference and cause a spark. So this is what happens to that excess charge. So here we've got the excess charge building up in the fuel, and then because it's attached to Earth, it will just flow nice and safely to Earth without giving it time for that charge to build up. No spark, no explosions. So all the key words there for this are highlighted, and try, if you ever get a question about refueling and safety, mention as many key words as possible. Okay, so operating theatres. Well, operating theatres are potentially very hazardous places because the anaesthetic that's used is often flammable, and any sparks there could cause an explosion. And when people move about in their scrubs, usually man-made fibres, and if they're rubbing against skin or their clothes underneath, you can imagine that a build-up of static charge will take place. And if they're in an operating theatre with flammable gases around, a spark could easily ignite them and cause an explosion in the operating theatre. So what's required here is a discharge before that voltage, that potential difference, gets large enough to cause a spark. And the easiest way to do that is to have an earthing issue. So you've got to try and earth everyone that's in that operating theatre. So rather than having a wire going from them to the earth, which would work, instead they add special conducting floors to the operating theatre. So as soon as any charge builds up on people inside the operating theatre, that charge is going to easily flow through them, flow down to the earth, through the conducting floor, and no spark will take place. And so the potential difference doesn't have a chance to build up to cause a spark. And that's that danger averted. So, I hope you found that episode on dangers of static electricity useful. Don't forget to subscribe to the channel where you can find out more about static electricity and other topics, and hopefully that will improve your understanding and get those grades boosted for you. And see you next time on Spiral Education.